Welcome to Brain Vision.
This is chapter 27, problem number 34. We are given a current carrying wire, and we're looking at the interactions between this wire and the Earth's magnetic field. So in part A, the Earth's magnetic field is given to us along, let's see if this is north, this is south. The Earth's magnetic field is given to us along from south to north. And the orientation of the current carrying wire is given to us as from west to east. So, and we are trying to determine the magnitude of the force that the Earth exerts on the wire. So, in order to calculate that, as you know, the formula is the current times the length of the wire times the external B field. In this case, this B field is the Earth's magnetic field, and the sine of the angle between the direction of the current and the direction of the magnetic field. So in our case, the magnetic field is along from south to north, and the direction of the current is from west to east. So using right-hand rule, first of all, we can determine the direction of the magnetic force exerted by the Earth. So from right-hand rule, we can see that the FB is basically out of the screen, but right, it's or you can say vertically upward. So let's calculate the magnitude now. The current is given to us as 1.5 amps, and then we have the length of the wire, which is 2.5 meters, and then we have the Earth's magnetic field, but it's given to us in terms of units of gauss, and we want to convert that to Teslas. So it's 0.55 times 10 to the power negative 4 Tesla, right? So then from here, the force exerted by Earth turns out to be something very small. It's 2.07 times 10 to the power negative 4 newtons for this particular orientation. And now in part B, still our magnetic field is from south to north. So again, this is the direction of the B field. However, now our current is out of the page. So when that's the case, let's see from right-hand rule what the direction of the force exerted on the wire is. So then your thumb is along the direction of the current, the rest of your fingers are along the direction of the external B field. When you curve your fingers 90 degrees, you find out that F sub B is going to go from east to west, actually. So east to west to the left. And the magnitude ILB sine theta, as you can see, the angle between the two, angle between I, green being I, and B is still 90 degrees. So sine 90 is 1. That's why we only plug in for I, L, and B. So we're going to see that we're getting the same answer as part A. And now in part C, the orientation. Again, this is north, south. The direction of the field is still towards north, but the orientation of the current now is down from north to south. Again, the magnitude exerted by Earth, that's what E stands for, ILB sine theta. When we look at the angle between I and B in this case, you can see that theta is actually 180 degrees, and sine 180 degrees is actually 0, which means the magnetic force exerted by Earth in this case is 0. So therefore, no direction to determine either. In part D, we are asked if the Earth's magnetic field, 0.55 gauss, and the force exerted by the Earth's magnetic field, whether or not this is interfering with the household electronics. So in order to answer let's go back to our answers to part A and B. Let's see how small the calculated force was. It was something like 2.07 times 10 to the power of negative 4 newtons, right? That was a force. So it's a very small number. It's a very small magnitude. And also, let's look at the strength of the magnetic field of Earth, which is roughly half a gauss. And well, everyday household like refrigerator magnets have the order of 100 gauss strength in magnetic fields. So compared to that, Earth's magnetic field is very small. So no, it doesn't interfere with everyday household electronics.